We'll close this module by considering factors that tell us more about what happens during the course of a chemical reaction rather than just what the net change is from the beginning to the end. Our learning goals for this video will be to look at how energy varies during the course of a reaction and see what added insights we can gain from that. Now, let's consider enthalpy diagrams that we've seen before, and I want to talk a little bit about some of the limitations there. So these are diagrams that basically give us static conditions that tell us about the beginning and the end of a reaction. So I've drawn one here that simply shows us that we start with reactants at a higher enthalpy, at products are at a lower enthalpy, so the change in enthalpy is going to be negative. So this would be an exothermic reaction. The total enthalpy content of the system decreases, it releases enthalpy. So what this diagram basically tells us is what the enthalpy content is at the start of the reaction and what the enthalpy content is at the end of the reaction. And it gives us an idea of what the difference is. So it tells us really about the limits of the state function. But it's not really giving us more insight than that. And in fact, all we get from this is what the total energy change was during the course of that reaction, but not how it happened or anything like that. So we need something more. I would also say that there is something that's missing from this, and that is that we don't have any sense from this whether energy needs to be added to get a reaction started, to what extent are the reactants and products stable, or do they go directly into other things? What exactly is going on in this reaction outside of simply the energy difference between reactants and products? So we may want to generalize this picture a little bit. So what we've drawn here is an added coordinate in the horizontal direction that we have euphemistically called a reaction coordinate. We show the reactants on the upper left and the products on the lower right. Now, a key ingredient that's been added here is we show both the reactants and the products as being, if you will, in the middle of a valley. And that's important because we know from most chemical reactions the reactants are actually pretty stable until they react, and the products, when they're formed, are pretty stable also. So in other words, it's not like they're just going to go to products and then that immediately switches to something else. Usually it's going to stay as products. Now, the difference in the enthalpy between reactants and products is still reproduced here. It's basically the energy gap or the enthalpy gap between the bottom of the valley for reactants and the bottom of the valley for products. Okay, what we haven't described here so much, though, is the reaction coordinate. And this is an area where you'll have to be a little bit more understanding. I'm not going to tell you explicitly what a reaction coordinate is because it varies from reaction to reaction. And in some cases, we don't even know really what is a legitimate coordinate that would carry a reaction forward. But what you can think of is that moving from reactants to products is going to occur on some kind of energy surface that tell us about the evolution of a reaction. That's what we're after in this kind of diagram. Now, it's one thing to look at this static picture. Let's look at another way of representing the same thing that might make a little bit more sense. We're going to represent energy variation qualitatively now, where we're still showing where the reactants and the products are in the same places, and we're still going to measure their energy relative to one another here as delta H, and it's still going to be exothermic. But there's a lot more in this picture now that we didn't have in the earlier one. For one, we can see that in order to get from reactants to products, we had to go over some kind of energy hill. And in going over that hill, we had to add energy to the reactants before we could get all that energy back from the exothermic process. Well, that place where it goes over has a special name. We call it the transition state. It is the state where you're making a transition from reactants to products. All right, and the location of that is one that it looks very simple the way it's located here, but if we have a complex reaction, it may be a very complicated function of the different bond lengths and bond angles and so forth of our reactants and products. So it's not something that's always, it's not always easy. In fact, it's almost never easy to exactly specify what that transition state looks like. Now, the energy that goes from the reactants, so the top dashed line, up to where the transition state is, is also one that we pay attention to. We call this the activation energy. Okay, it is the energy that somehow the system must accumulate, either from collisions or some other means, to get over that transition state barrier so that it can make a transition from reactants to products. We're going to talk about this a lot more when we get into Module 7 and perhaps a little bit in Module 8 as well. So I want to plant this seed now so that you've seen it before. We'll talk about it in more detail then. But I'll just say that the activation energy is something that really helps determine how fast a reaction will happen. It doesn't affect whether it's exothermic or endothermic, but it will tell you how fast a reaction may happen. All right, so that's enough of reaction energy diagrams. We're going to see these and some other similar ones as we go through the course from here on out.